Hello, good morning to everybody. Today is the third class of Physics 2. We will discuss Gauss's law and its application. Actually, before knowing about Gauss's law, we have to discuss about the electric flux and the electric field. In our previous lectures, we have discussed about the electric flux uh, and uh, electric field with the graphical representation. So today we will discuss the Gauss's law and its application. Actually, the Gauss's law states that the electric field coming through a certain area is proportional to the charge enclosed. And this is the mathematical representation. So actually, this is the mathematical representation, and this is the statement of Gauss's law. What does it mean, and how do we use? So first of all, we will discuss what is the actually electric flux. First of all, I want to review what is the electric field lines. Actually, electric field lines convenient for visualization electric field patterns, line pointing in the direction of the field vector at any point. The electric field vector is tangential to the electric field lines to each point. In previously, we have defined this two item. The number of lines per unit area through a surface perpendicular to the line is proportional to the strength of the electric field in the given region. So we can define these three as a previous lecture we have noted. So the electric field from A to B, like this, electric field pattern for a positive point charge, the lines will radiate outward equally in all directions. And for negative point charge, the lines will point inward equally in all directions. That means from negative charge, it will be inward, and for positive charge, it will be outward. You have to remember this one, like this. For positive charge, that means outward for the positive charge, and for the negative charge, it will be like this. That means inward. So in previous lecture, we have discussed in a greater detail like this. So an electric dipole consists of two equal and opposite point charges, and the number of field lines leaving the positive charge equals the number of lines terminating on the negative charge. So for two equal and like point charges at a great distance from the charges, the field would be approximately that of single charge of twice q of the lines between the charges. That means repulsive, because for two equal but like charge, this is why there will be repulsive force of attraction. So first of all, what is actually electric flux? Electric flux, we must know electric flux is the product of the magnitudes of the electric field. So electric flux is the product of the product of the magnitudes of the electric field. Electric field that we have defined in our previous slide, the and the surface area and the surface area the surface area a perpendicular to the field, a perpendicular perpendicular to the field is E equals to electric field multiply area. And units will be what? Newton meter square. Units will be meter, Newton meter square per Coulomb square. So actually the electric flux is the product of the magnitudes of the electric field. This is the electric field magnitudes, and this is the vector field, and the surface area. This is A is the actually surface area. So the electric flux can be denoted by this product. This is the actually dot product, because it will give the magnitudes. This is why we can denote as a. So symbolically and graphically we can represent like this. So the electric field, electric flux is the product of magnitudes of the electric field and the surface area, a perpendicular to the field. That means if we take the area like this is the area. So all the electric line of force will make the electric flux. Okay. So it is denoted by capital E vector. So phi E is the electric flux equals to electric field dot the area. So this is the actually in figure representation of electric flux. So the electric flux and general area, what will be electric flux and general area. The electric flux is proportional to the number of electric field lines penetrating the some surface. Okay, this is actually penetrating the electric line of forces, and the whole electric line of force will make the electric flux. If more the electric flux, and the number of electric lines also will be more. So the number of field lines that go through the area perpendicularly is the same as the number that goes through the area A. Okay, the field lines may make some angle theta with perpendicular to the surface, then the electric flux can be denoted by for the theta angle A cos theta. And this is the graphical representation. So the electric flux, interpreting the equation, the flux is maximum when the surface area is perpendicular to the field. That means if theta equals to 0 degree, then cos 0 degree equals to 1. This is why theta equals, we get the maximum electric flux. The flux is 0 when the surface is perpendicular to the field. That means if theta equals to 90 degree, then we must know cos 90 degree equals to what? 0. So if the field varies over the surface phi, then phi equals to electric flux equals to A cos theta is valid for only a small electric element of the area. So the electric flux in general form we can denote in the more general case. Look at a small area element del phi. Okay, for the electric field, for the field E equals to EI del I cos theta I. That means EI dot del I for a small area. Okay, for a small area we get del AI, and theta will be theta I. For this we get the electric field capital EI. So in general becomes, we can if del I tends to 0, if a small area tends to 0, and the sum of all this area will be, we get a limit which will be the actually surface integral. If we remove the limit, then we get the surface integral, because electric field dot dA will give the double integral. So surface integral. The surface integral means the integral must be evaluated over the surface in equation. So in general, the value of the flux will depends both on the electric field and on the surface. Okay. So the electric field makes an angle theta I with the vector del AI, defines the being normal to the surface element. So the electric flux and closed surface. Suppose for this theta angle and for the rotation and for another rotation, actually this is the whole body, and we consider some surface. So assume a closed surface. This is actually closed surface. The vector del I point in different directions. So at each point, they are perpendicular to the surface. By convention, the point outward. Okay, this is the electric field E, electric field E, and electric field E for the small area of this whole closed surface. So flux through the closed surface, electric field flux through this area element is negative. Okay, because theta is more than 90 degree, and the electric flux through this area element is 0 because angle is 90 degree. So cos 90 degree equals to 0. This is why. And the electric flux through this area element is positive because less than 90 degree. So for these three condition, we get these three. The field lines are crossing the surface from inside the outside. Theta is less than 90 degree. So phi is positive, and field is graze the surface because the angle is 90 degree, because cos 90 degree equals to 0. So flux will be 0. The field lines are crossing the surface from the outside to the inside about 180 degree. That means theta lies between 180 degree and 90 degree. So phi is negative. So electric flux will be negative for this. So flux through closed surface, finally we get the net flux through the surface is proportional to the net number of lines leaving the surface. So we get the total number of flux of the surface. We get proportional to the net number of lines leaving the surface. Entering line of forces equals to the leaving line of forces. This net line number of lines leaving the surface minus the number of entering the surface. So if En is the component of the field perpendicular to the surface, then we can get the our desired equation phi E equals to surface integral. This is the closed surface, so closed integral E electric field dot small area. So we get this one. The integral is over a closed surface. We have to remember this one. So flux through a cube, the field lines passes through the two surfaces perpendicularly and are parallel to the other four surfaces. That means for phase one, we get this is the phase one, and this is the phase two, and this is the phase three, and this is the phase four. So for cube, there are four phases. So for phase one, electric field equals to minus E L square. And for phase two, E L square is since this is the positive, about less than 90 degree angle will be, and for other two sides because equals to cos 90 degree equals to 0, so you get equals to 0. So the total surface, total electric field will be 0 if we sum for four surfaces. We get the total electric field will be 0. Actually, Carl Friedrich Gauss, we are discussing the Gauss law and its application, actually contribution of this great man, great scientist and mathematician, made contribution electromagnetism, number theory, statistics, non-Euclidean geometry, commentary, orbital mechanics, a founder of the German Magnetic Union, studies the Earth's magnetic field. So this is the Carl Friedrich Gauss, a great mathematician and physicist. So now we will discuss the actually what will be the Gauss law and what's the Gauss law. So we have discussed about the what is electric field, and now we will try to understand what will be the Gauss law. So the Frederick Gauss, the mathematician and great scientist, he was the contemporary of Charles Coulomb. Instead of finding the field from a single charge, Gauss found the field from a bunch of charges. That means there is a similarity with Charles Coulomb. To Charles Coulomb for a single charge or point charge, but Gauss law for a bunch of charges. That means a big amount of charges. So why is actually Gauss is law is important? Specifically, Coulomb's law finds a field or charge, point charge from a point charge. We get a field or charge from where? Point charge. Coulomb's law. In general, Gauss law finds a field or charge from any charged objects. That means a bunch of charges, a big amount of charges. Gauss law can be applied for a bunch of charges, but Coulomb's law can be applied for point charges. So this is the main difference. What is the Gauss law? Said the electric field coming through a certain area is proportional to the charge enclosed. That means Gaussian surface, because we are discussing about the Gauss law for a bunch of charges. So a bunch of charges or a big amount of charge will be exist in a surface, which is called Gaussian surface. An imaginary surface around a charge distribution group of charges arbitrarily chosen for its symmetry. So the electric field coming through the imaginary surface is fairly constant through all areas of the charges. For the point charge, specifically for Coulomb's law, we can denote the electric field like this. But for OR, and this is the cylindrical, so 2 pi r is will be the surface area. And for a sphere, the surface area will be what? 4 pi r square. Strange shape like this. Strange shape, we have to use the calculus for to find out the whole surface, because it is the actually non-uniform surface. And parallel plates, for parallel plates, we have, especially for capacitor, we have to use the surface area like this, length multiply width. Now, what is Gauss law? The electric field coming through a certain area is proportional to the enclosed charge. That means charge enclosed. Electric field. Quick reminders on electric field lines. More field lines equals to stronger field. Many field lines will make stronger field for the electric field. Field lines always come out of the surface perpendicularly from positive into negative charge. So the direction positive charge will move. Charge enclosed. The field is proportional to the charge inside the Gaussian surface. More field lines equals to stronger field lines and stronger charge inside. So what is actually Gauss law? The electric field coming through a certain area is proportional to the charge enclosed. That means the surface area we have denoted, actually this is the closed integral E electric field uh, dot with enclosed area, small area dA, which is proportional to the total amount of charge in the Gaussian surface. How do we make this in equation? And we have to remove this proportionality, we have to use a proportional constant, can be denoted by small c, where we can choose small c is equal to 1 by epsilon naught. Okay, but epsilon naught means what? Permeability constant. It is a constant, it 0.854 into 10 to the minus 12 Newton meter square per Coulomb. And we can choose k equals to 1 by 4 pi epsilon naught, which will be the Coulomb's constant. Okay, Coulomb's constant, and it is equals to 8.99 into 10 to the 9 Newton meter square per Coulomb square. So this equation of the electric field can be written as q by epsilon naught. And this is the actually Gauss law for a bunch of charges in a Gaussian field. How much field through a certain area? We have to rename this is to the electric flux. This equals to actually electric flux, and how much field comes through a certain area. Okay. So finally, Gauss law summarized as the electric field coming through a certain area is proportional to the charge enclosed. This equals to electric field, total electric flux or electric field equals to surface area equals to q by epsilon naught, where phi e equals to electric flux field through a whole area of the surface, and capital E is the electric field, and A is the area, and Q is the charge in object, actually capital Q. This is the charge in object, a bunch of charges on Gaussian surface. Epsilon naught is the permeability constant. Okay, now we can discuss some quiz type problem, a sample of problem. A banded graph machine with a radius of 0.25 meter has been charged up. So total amount of charge within the area 0.25 meter. What is the electric field 0.1 meter away from the center of the sphere? Actually, we can hints here where are all the charges on the outside. So how much charge is in the center? Actually, electric flux can be denoted by 0 divided by, because total charge is 0. So we get 0 since all charges is on the surface. So in center, actually there are no amount of charges. So the total amount of charge equals to what will be 0. Okay, this is the a quiz for you. For the sample problem 2, find the electric field around a point charge. Actually, for it will be suitable for Coulomb's law. Remember, the area of the sphere Gaussian surface will be 4 pi r square, and EA equals to what will be Q by epsilon naught. Total electric flux. So total electric flux around the area 4 pi r square equals to Q by epsilon naught. But E equals to Q divided by 4 pi epsilon naught square. Uh, this is for what? Coulomb's law. Don't forget K equals to 1 by 4 pi epsilon naught. Okay. So E equals to small k Q divided by R square. What does this look like? Coulomb's electric field for point charge. Remember, we have to remember that this will be applicable for only Coulomb's law. Another one, sample problem 3, a solid sphere of radius 40 centimeter has a total positive charge of 26 microcoulomb, uniformly distributed throughout its volume. Calculate the magnitudes of the electric field at the following distance from the center of the sphere. So from the center, 0 centimeter and 30 centimeter and 60 centimeter. There are three conditions. So for 0 centimeter, you can calculate inside the sphere Q equals to 0, because all inside the center total amount of charge will be 0, because all charges distributed uniformly on the surface. So phi E equals to EA equals to Q by epsilon naught, total Q equals to 0. For this electric flux will be, magnitudes of the electric field will be 0. Now for the within 30 centimeter, still inside the sphere, all will be total amount of charge will be 0. So and the in this case we can also 0. Similarly for 60 centimeter, 60 centimeter electric flux around the surface Q by epsilon naught, but radius what will be 0.6, 0.6, because the radius are equals to what was 40 centimeter. Okay, so but around the 60 centimeter we get the electric flux this, and within this also through center, because 30 centimeter within. Before discussing the Gauss law, we have discussed about the electric flux. First, we need to concept of electric flux. Suppose this is the area, this is the area. So for this one, we can get the electric field like this for this area. And flux is just electric field times area. Electric field, flux equals to what will be electric field multiply total area of the surface. Now, first we need to, if electric field does not pass through the area, flux is 0, because cos 90 degree equals to 0. Similarly, in general, we use a normal vector to the plane A vector like this. For more general, the angles, the flux varies as cos theta. Okay, cos theta we have discussed about cos phi equals to EA cos theta. That means a dot product of dot vector dot product. Similarly, for general three cases, we have discussed about this for theta equals to 0 degree and theta equals to acute angle and theta is equal to right angle. So for we get the total electric flux equals to like this. Now total flux through a closed surface I have discussed also this. We use the convenient that the normal way points outward. There are four faces, and for four faces, we get the total electric flux equals to 0. And for the top, for the positive, and for the bottom, negative, because it's the about 180 less than 180 degree and greater than 90 degree, and total flux will be 0. We have discussed about this. So what does the integral mean? The circle indicates an integral over the closed surface. This is the closed integral or contour integration. So in practice, we will not leave the not have to evaluate the interval. We break the surface up into section where the flux is easy to calculate. So principal sum over the infinitesimal elements dA. That means total area can be divided into small area dA. So we get the actually the full Gauss's law like this. The left side is the total flux out through the surface, and the right side is proportional to the charge q inside the surface. So the constant epsilon naught is the usual vacuum permeability. So how do we use it? For example, consider the charge q, and which is a spherical sphere whose area is 4 pi r square. By symmetrical, the electric field must be directed radially outward for the positive charge, for negative inward, and for positive charge outward. The magnitudes of the electric field must be constant on the surface. The flux is just EA, electric field multiply enclosed area. So Gauss law gives E equals to Q by epsilon naught. And electric field, electric flux around the surface 4 pi r square equals to Q by epsilon naught. So E equals to, we get actually Q divided by 4 pi epsilon naught r square, which is actually Coulomb's law. And for this one, with the radius r, we get this one, and out greater than radius, we get actually amount of charge will be 0. So general choose a surface corresponding to the symmetry of the problem. Break the surface up into the subsurfaces where the electric field is either constant and parallel to the normal and perpendicular to the normal. Evaluate the total flux using the electric field as free parameter. Solve the Gauss law for E. So this is actually what does it mean? What is the actually electric flux? So the statement of the electric field for Gauss law, the electric field coming through through a certain area is proportional to the charge enclosed. Charge enclosed. So this equals to small area. This is the total electric field or electric flux due to the electric field will be the proportional to total charge q, and this can be written as equals to small c q. We can take small c as 1 by epsilon naught. This is the proportionality constant for this. So we can write this equals to Q divided by epsilon naught, where epsilon naught is the permeability constant, which is equals to, this equals to epsilon naught equals to what will be 8.854 into 10 to the power minus 12 Newton meter square per Coulomb square. And we also know another constant, Coulomb constant, K equals to 1 by 4 pi epsilon naught. So we can write this epsilon naught equals to what will be Coulomb for the Coulomb's law. So this is actually Gauss law. Okay. So this is the actually electric field coming through the certain area dA is proportional to the charge, and epsilon naught will be multiplied with this. Then it will become the total charge. Now we'll try to derive the Gauss law for a positive charge. If we take a surface this like this and a small charge Q plus, this is a positive charge. If we consider a small area like this, small area, and perpendicularly this will be En, electric field, around the dA. This is the dA, small area, and another will be electric field, total electric field, and this is the around the angle theta. So this is the small area dA. We take the small area dA, and we can take this sum. So this is the whole surface and Gaussian surface. Actually, the electric field E at every point, derivation of Gauss law. The electric field E is E at every point of the surface. So for this, we can, from the charts, and magnitudes at the point R. So by the definition from the for previous lecture, by the definition of electric field E equals to, by Coulomb's law, we can write actually Q divided by 4 pi epsilon naught R square. This is equation number 1. This is equation number 1. Now for the infinitesimal area, for infinitesimal area, the whole area, we can divide it into small area dA. This is the infinitesimal area. The magnitudes and the direction of the electric field will be same for this area. The component of E, the component components of E will be what? Actually, component of E will be along the base will be E cos theta along the base E cos theta. So components of E is En equals to what will be E cos theta. But along the perpendicular E sin theta will be balanced, and theta is the lies between normal between E electric field E and the outward normal to the surface. Okay, so this is the actually electric field along the E base E cos theta. Now En electric field along infinitesimal area dA equals to what will be equals to E and equals to what will be E cos theta by equation 2 dA. Okay. By equation 2, and this equals to E cos theta. Actually, we can use by the formula this one Q divided by 4 pi epsilon naught R square. Actually, this distance will be R. This distance will be R. So we get actually dA cos theta dA. Just putting the value of by equation 1. Okay, by equation 1 we get this one En dA. This is equation number 3. Again, dA cos theta is the projection of dA along the radius vector r. That means like this, what will be the projection dA cos theta. This is the dA cos theta projection along the radius vector r. Okay, this is the projection. So from the vector representation, we can write dA this divided by r square will be angle d pi. The element of solid angle subtended by dA. This is the solid angle. The element of solid angle. You must know solid angle equals to total solid angle equals to 4 pi steradian. You must know. Therefore, from equation 3, En dA equals to Q divided by 4 pi epsilon naught cos theta by dA cos theta by r square. dA cos theta by r square d pi d omega. Now, if we take the integration E and dA equals to, all are constant, 4 pi epsilon naught dA cos theta by r square, this d omega. You must know this total angle, solid angle will be 4 pi epsilon, 4 pi steradian. So we get this value equals to, what will be this value? D omega. For a small uh, infinitesimal area dA, we get the solid angle d pi. So this integration will be q by 4 pi epsilon naught. This total angle will be 4 pi. So 4 pi will be cancelled. So we get only q by epsilon naught. Since total angle will be what? Total angle for infinitesimal area dA will be, give the total angle 4 pi steradian. 4 pi steradian. So hence we get closed surface area equals to q by epsilon naught. This is the actually Gauss law. This is the Gauss law. We have derived it. So this is the derivation of Gauss law for in an infinitesimal area dA and for the whole surface. This is the Gaussian surface. So the electric field will be E at every point of the surface from the from charge q plus, and this we selected a small area dA whose magnitudes at the r point will be, the electric field will be this. By Coulomb's law we got this one. So for infinitesimal area dA we get the uh, vector field. There will be two components, one along the we get the two components of electric field, one along the one along the base and another one along the perpendicular. So along the base will be what? dA cos theta. Along the perpendicular, that means normal, dA sin theta. But dA sin theta will be balanced each other. This is why only effective electric field will be En, and which will be E cos theta. So En d multiply small area will be like this. Just putting this value E, we get equation number 3. Now dA cos theta is the projection of dA. Projection of what? dA along R. This is the projection of dA along R. So this will be angle theta, and dA cos theta is the projection of dA along R. So dA cos theta by R square equals to d omega. This is the angle which is called the solid angle for the infinitesimal area dA. Now En dA equals to, by equation number 3, we get q by 4 pi epsilon naught by R square. Just putting this value dA cos theta by R square equals to what? dA cos theta by R square will be, cos theta by R square will be what? This. Now taking closed integration, contour integration on both sides, we get q by epsilon naught, which is actually Gauss law. And now the application of Gauss law First of all, the deduction of Coulomb's law from Gauss law. It is one kind of application. So Coulomb's law can be deduced from Gauss law and symmetry considerations. Suppose we can take a point charge in the center Q. If we take a small surface area, this small area will be dA, and the electric field due to this infinitesimal area dA will be E. The spherical and this is the Gaussian spherical surface. Let the electric field is E, normal to the surface, normal to the electric field is E, is normal, which is normal to the surface, and is constant in magnitudes for all points on the surface. Okay. So hence by Gauss law we can write product of electric field of the infinitesimal area D, total surface area will be, can be written as like this. Equals to Q by epsilon naught. This is equation number 1. Since total area equals to 4 pi r square, that is total surface equals to 4 pi r square. So from equation 1, we can write the surface area E dA equals to P into total area E into 4 pi r square. This equals to equation number 2. So from equation 1 and 2, actually these values are same. So we get E into 4 pi r square equals to Q by epsilon naught. So E equals to what will be? Electric field Q divided by 4 pi epsilon naught r square. And this can be written as Q divided by 4 pi epsilon naught r vector divided by r cube. This is the vector form of electric field according to the Coulomb's law. So the Coulomb's law can be deducted. Hence, Coulomb's law can be deducted from Gauss law and symmetry consideration. Similarly, we get the Gauss law from Coulomb's law also, because Coulomb's law was invented before Gauss law. So this is the one kind of application of Gauss law. There are many other applications. We can apply Gauss law. Suppose electric field due to the charge sphere, to find out the electric field from the charge sphere. We can another number 3. We can apply Gauss law, electric field due to the long charged cylinder, to find out the electric fields due to a long charged cylinder. We also can apply Gauss law. So, so today we have discussed actually what is electric flux, and what first of all, what is electric force or electric line of forces, what is electric flux, and we have evaluated the electric flux for 3 types of angle. Okay. Then we have defined Gauss law. So I hope everybody will enjoy this class and watch everybody. So thanks to everybody. Finally, we have discussed about the Gauss law. Actually, Gauss law indicates the electric field coming through a certain area, which is proportional to the charge enclosed. And this is the summary of this class.